Hi, I'm Dr. Kasim Rafiq from the University College London, the Department of Biochemical Engineering, and I'm a senior lecturer in the bioprocessing of regenerative medicines and cell and gene therapies. The OMMS project is really trying to redefine the scope of manufacturing of cell and gene therapies. At the moment, we have a process where we take the cells from the patient, we have to take it to the lab, manufacture their cells, do the gene editing, and then reintroduce back into the patient. That's been clinically proven, and it's had some fantastic case studies and successes, but it's very expensive. That process of taking things from the patient and into the lab environment is hugely costly, and it has many issues around contaminations, logistics, and how you get the cells to and from the patient. And what really excites me about OMMS is the fact that we have the opportunity to really redefine the whole manufacturing landscape and rethink, how can we develop new therapies and effectively really reduce the cost of these therapies and make them widely accessible.
Hi, I'm Rob Barker, a lecturer in chemistry at the University of Kent. So for me, the exciting thing about the OMMS project is taking a completely new perspective on what we're trying to do with biomanufacturing, particularly looking at CAR T-cell therapy and the manufacturing of that in the future. For me personally, my role within that is we're interested in the understanding and the studying the biological systems we're looking at. So if in this case we're interested in the CAR T cells, we're interested in working out how we can separate those from whole blood. We have a vision of being able to take that manufacturing process and putting it onto the body so that it's continually doing this. So we need to have a way of being able to integrate that into our bloodstream, into our peripheral bloodstream. So if we do that, that comes with its own challenges of understanding how we can integrate that, designing the materials in order to cope with that. The next step, we then need to be able to separate from that blood. So we need to characterize what we need to separate, and we need to use clever design of microfluidics and clever design of using the chemical and the physical properties of what we're using, of what we're wanting to extract, to actually use that and separate them. So that's my core role in the first stage of that process, and then we want to actually do something with those T cells. And that's where we're interested in using different ways of creating little holes inside these cells in order to be able to insert things in for us. And we're going to explore a number of different ways in order to do that, to see which would be the best for this small kind of on-body device for manufacturing.
Hi, I'm Rob Hewson. I'm a senior lecturer from Imperial College, and my main focus on this project is to do with modelling and really solving equations to assist in the design of the device. My group has got expertise in optimization, and hopefully we can bring that to some of the modeling, whether it's the flow device, whether it's the way of getting the DNA or the RNA into the cells, or whether it's supplying the fluid back to the patient. I think there are a number of key challenges. In terms of the flow device, it's really trying to get the throughput, being able to identify cells, being able to alter cells, and being able to supply cells reliably to the patient. I think this is, there's a whole number of challenges in design optimization, fluid dynamics, and some of the complex fluid dynamics, the complex rheology, and trying to look at how we can optimize the flow device are going to be really significant challenges. And hopefully we can bring some of our formal optimization work that we've been doing to bear in order to solve this problem.
Hello, I'm Philip Stanley Marvell. I'm a university lecturer at the University of Cambridge. So in the project, I'm responsible for the electronics. The control system from biometrology eventually controls the electroporation system. The electroporation is responsible for introducing the genes into the T cells. Now, once we have the delivery of that therapeutic within the on-body manufacturing system, it will also be necessary to monitor the entire system and to get information from the on-body factory to, say, a clinician. Are numerous challenges. So interfacing the sensors, which are going to be produced by our colleagues at Bath, interfacing the signal processing to the therapeutic manufacturing, and also the communication of the information generated by the on-body system to the clinician. Being able to do all of that within the power envelope of a system which is going to be worn, to be able to do that within the thermal envelope of a system which is going to be on-body, and to be able to eventually have this entire system powered off energy generated, hopefully eventually by the human body. So that's all going to be very challenging.
So my name is Mirella Di Lorenzo, and I'm a senior lecturer at the Department of Chemical Engineering, University of Bath. Okay, so I will be leading the work package that is focused on the design and development of sensors for biometrology, so for the monitoring of specific biomarkers that are related to the activity of the cells. And the other thing I'll be involved in is on the design and development of a chip that will be used for the growth and differentiation of the cells. And the chip will of course contain the sensors that we are developing.
Hi, I'm Glenn Parry, Professor of Strategy and Operations Management here at Bristol Business School. So my main role in this is supporting the business model that's ensuring that the value proposition, that the use of the offer and the cost are all matched. I'm particularly interested in ensuring affordability. With regards to the design, we are process mapping. We're trying to ensure that the different elements of the device naturally flow together, because ideally we'd seek to create a therapeutic device that is modular, so it can deliver a number of different therapies and we can change it over time.